So if you want to join a nitrogen to an aromatic system, then you need the aromatic system has to have a leaving group like a halide, and then it fits into the Buchwald-Hartwig set. Okay. Can you see if you can write out how this conversion of this ene into this diene goes? See if you can remember there the sets of cycloadditions, cycloreversions, different cycloadditions and so on to get to that ene product. This is what we were doing yesterday afternoon. So for the Grubbs catalyst, I would just draw ruthenium, the ruthenium carbene. Don't worry about the other ligands that are there. Remember, your ruthenium carbene is likely to add to the alkene first. Okay, I'm going to talk it through now. Hopefully you can follow. You have a ruthenium lined up here. I'll put the ruthenium joining to the inside end of the alkene. So you make a 4-membered ring here. That breaks down instead of the way that you formed it, breaks down the other way, and that gives you styrene coming off here, but what it gives you is off this carbon, it's left now as a ruthenium carbene. So if you like, I could redraw it with ruthenium at the end here. That adds to form a 2 + 2, a 4-membered ring across one of the pi bonds of the alkyne. And if you break that down to form a new carbon-carbon bond, then that leaves one carbon left over, which is now a ruthenium carbene, and can do the same thing with the ethene that's there to chain extend the side chain. Now I don't know how much that makes sense, but it's a succession of 2 + 2 4-membered ring formations which form one way round and then break down the other way round. So I would put the ruthenium on the left-hand end at the bottom here, the carbon at the right, and then break it down to give a ruthenium carbene on that side chain. Then that adds across the alkyne. Again, that breaks down the opposite way to the way it's formed, and that gives you the 7-membered ring with a ruthenium carbene at the top here, which then does metathesis with the ethene that's present. Now, does that make sense to those of you who didn't get that far? With all of these metathesis sequences, it's always taking a ruthenium carbene and adding it to form a 4-membered ring with one of your multiple bonds. You add it one way and then you break the 4-membered ring down the opposite. You form 2 bonds to make the 4-membered ring, then you break the other 2, break it down, and then just keep going that way. If you have a look back at the general schemes, you'll see how that happens. In fact, let me find it. Okay, so here it is in a general scheme. You've got some linking groups. You've got an alkene, which was in the bottom chain in the example of the problem. You've got an alkyne in the top chain. So we add the ruthenium to the alkene. And again, notice the ruthenium is best added to not to the terminus of the alkene, but to the inside end. You form a 4-membered ring, you then break it down the opposite way. So the way you had an alkene, you now have a ruthenium carbene. That adds across the alkyne to give a new 4-membered ring. That was formed by making the top and bottom bonds. If you now break it, to break the left and right hand bonds, then what you end up with is forming a bond to close, a double bond to close the ring, and a side chain which now carries the ruthenium carbene. And then that does the metathesis with ethene to finish it off. So there was ethene in the reagents. So if you didn't see that all the way through, this is the one. This is the page to refer back to. But I think some people had that. So you see, this is a general case, but the problem is applying it in a real molecule. The linking tether is obviously a little bit more complicated, but it's the same basic principle. There it is. Alkene, alkyne, linking groups. So the key is to remember always that you have a ruthenium carbene, a ruthenium double bond to a carbon of some sort to start this off, and just keep adding that to alkenes. Add it one way to form a four-membered ring, break down the four-membered ring the other way, add it to something else, break it. So you just keep going like that. So even if you've never seen the reaction before, if you remember the basics of the sequence, you should be able to follow it through, hopefully. Now, we won't bother with the conversion of A to C there, but let me find another problem now. Okay, now this is a big ring molecule made by Professor Nicolau, whose name we've seen already in the endiandric acids one. Look at what's happening. There's two iodoalkenes here, and look at what you've got to fit in to close the ring. So have a think about, or a suggestion about what kind of reagent you might need. That's the palladium, yeah, so we need a palladium zero catalyst. But how many carbons have we got to add in? How many carbons are missing? 2, yeah. Then which are conveniently numbered 19 and 20 in the product. So if you look, that's a triene system in the product. We've got a diene, we've got 2 alkenes in the precursor. So we can't join them directly because otherwise we'd end up with a diene. So we need to be able to put 2 carbons in there. So what would you suggest as a way of those 2 carbons to join? Which Wurtz reaction? Oh, we haven't talked about that this week. It's a modern, yeah, but right. Effectively, it is a modern version of the Wurtz reaction. But what out of the ones that we've done this, and the Wurtz reaction will be dissolving metal, it would be a little bit vigorous for the rest of the molecule. So of the reactions we looked at in yesterday and today, in fact go back to yesterday morning, what do you think we should do? We've got two alkenes with leaving groups on. Sorry? Yeah, with the palladium catalyst. Yeah, well, what is the 2 carbons going to look like? I mean, it's not just ethene you're going to add in there. Right, a coupling reaction. Well, what would we need for the? Give me some suggestions for what we could use for the 2 carbons of the coupling reaction in the coupling. Sorry. already got the halides. So what were the suggestion? What were the possibilities for? What were the possibilities for the other parts? No, that's for alkynes. You're getting, yeah. We want to put an alkene into the middle there. But what would we need on the alkene to make it couple to an alkenyl iodide? We could use a magnesium one. That will be the Kumada reaction. What else did we see? We could use the Heck reaction, yes, you're right. I wasn't thinking of that. So what else, along with the Kumada reaction, what else was in that group? That was magnesium on your alkenes to get it to add. That might be more tricky to get because you want 2 carbons with a Grignard reaction at each end. That might be a bit tricky to make that compound, but in principle that could work. So magnesium, what other metals or pseudo-metals did you see?
So
Tributyl tin, yes. And that is exactly what Nicolau used. Now, I would never expect you to guess these conditions, but the key was what the guy at the back said there, a palladium 0 reagent. And this was done using a double Stille reaction. To make this kind of molecule with magnesium each end just might be a bit too unstable actually. You could do this with a boron group at each end, so do a Suzuki type reaction, but to use magnesium or zinc, it would probably be a bit too unstable. But tin or boron, with the various possible substituents on the boron, but tin or boron, so Stille or Suzuki couplings would be okay here. So you're right when you suggested tributyl tin, yeah. Now, notice the yield of this reaction is not fantastic, but when you think about forming that big ring, it's perhaps not too surprising that this is not very high yield. Why do you think this was done at 0.01 molar solution? Why do you think it was done in dilute solution?
Because polymerization unless with stiffness.
Yeah, because otherwise, if it was not in high dilution, then you do, let's say one coupling happened, then you've got this joined to that, you've got the other end ready to couple. Maybe it couples with not this alkenyl iodide, but one in the next door molecule. So, and then that goes on and you end up with a polymer. What you want to make sure is the thing it meets first, once you've done one of the 2 couplings, the thing it meets first is the other alkenyl iodide. So often with these large ring systems, forming in the large rings, you need to do it in high dilution because there's too much flexibility, so you need to make sure that the chance of it meeting another molecule is lower than the chance of meeting the other end of the same molecule. So that's why this is done in high dilution, and that's another contributing factor to a lower yield. There may be some polymer there. I'd have to go back to the original paper in 1993 to find out whether there was polymer or other side products formed. So I think that's, I call it a stitching step because that's what Nicolau called it. He made the thing and then he stitched in at the final piece. So you see two alkenyl iodides there. You should think of a coupling reaction, as somebody said. We've got the leaving group, so we need the organometallic bit on the other end. So tin or boron will be good, because you're likely to be able to form that in stable form. And then you need some kind of palladium zero catalyst. And I suspect a lot of catalysts were tried before coming up with that one. That's actually a palladium 2 catalyst, and that is that is reduced by the tertiary amine base, Hunig's base. And if you look in some textbooks, you'll find out how tertiary amines can do a reduction of palladium 2. The thing that the tertiary amines can get oxidized to an imine. It's a very hairy mechanism, but it is known that that will happen. Like triphenyl phosphines can reduce palladium 2 to 0, amines can do it as well. So it is still a palladium 0 process. But you look at those conditions, you can imagine quite a lot of things were tried before that one was arrived at. Okay, so you see two alkenyl iodides, so you should be thinking of a coupling reaction and some sort of palladium 0 catalyst. Okay, look at that one, and again, this is a little bit less complex. This is, you see in a sort of pinky colour here, the bond you're trying to form. So what would be the two components you would need to do that via a Suzuki-Miura coupling? In fact, it's something you can make in a single step from here and in 2 steps from there for the 2 components. So it's another coupling reaction. Now, if we're thinking of the Suzuki-Miura coupling, yeah, we need something with a leaving group on one side, like a halide. What's the organometallic bit? Boron, a boronic acid, or some derivative of that. So looking at these two, which do you think is likely to be the leaving group, the one with the halide on? The first one, yeah, because we've already got a halide. What have we got to, why do you think we need to do something to this? Why not use it directly? What do you think we might have to do? Yeah. Right, we need to protect the OH to make sure that OH doesn't get involved in a Buchwald-Hartwig type coupling reaction. So we need to protect the OH, and you've suggested doing it with a benzyl group. But there could be others. In fact, it was a benzyl group, and because you can see that in the product here, can't you? BN for benzyl, CH. So benzyl chloride to react with. What will the other half need to be? A boron derivative, we've decided. So there it is. In fact, it was done the other way round. If you look at that, the obvious thing would have been to use the boron on the left, the bromine on the left, the boron on the right. But don't ask me why, but they did it the other way round. But it is a perfectly good guess to say if you've got the bromine there already, let's use that as the leaving group and let's put the boron on the other half. So I don't know why, I'm not quite sure why it was done this way round, but in fact they put the boron on this bit and protected. In fact, that must have taken more than one step, so that, yeah, a bit inaccurate there. And they made the bromine on the other side. It doesn't really matter, so this illustrates that you can put the leaving group and the boron, tin, whatever, on either way round. But quite correctly, if you see the Br there, you'd expect that to be used directly. However, that wasn't done in this case, so it's a little bit of a trick question, but nevertheless the principle is there. You need a bromine on one, or a leaving group on one side of bromine, and you need a boron derivative on the other, and it is actually a boronic acid. It's the simplest boron derivatives, the ones that were actually used first. And we do need to protect the OH group in the phenol, and you suggested that. Okay, so yes, it's the opposite way round to the way I would have predicted if I hadn't seen the answer before. It's the opposite way round to what you predicted, but that doesn't mean you're wrong. It just means they chose to do it the other way round. Okay. In fact, that class of natural products at the bottom right there is one that I've worked on, published a few papers on, but we've not been using this, we weren't using this strategy. Okay. Here's another one. Actually, I've written what is the coupling reaction. Strictly speaking, it's not a coupling reaction, but what is the organometallic reaction here? So we have alkenes. Well, yeah, I beg your pardon, it is a coupling reaction here. Yeah, sorry, it is a coupling reaction. Well, yeah, sort of. I guess it's not, yeah, okay. I suppose formally it's not a coupling. What were you suggesting earlier for one of the earlier ones? A Heck reaction, yeah. So that's so this is where the palladium will first add. It will add to that nearest double bond. Write down what you'd get if that first reaction happens as a first intermediate in a Heck reaction. So I think strictly speaking it isn't a coupling, so I wrote that wrongly, but it's an organometallic reaction. It is a Heck reaction. Write down what you get if you have palladium inserting into the where the triflate is, and then your organopalladium intermediate adds to the nearest double bond. You got something?
What is this GAN restriction GN?
Steric ammonium nitrate.
In the first step of hydrogenation, then there is hydrogenation at the one this was
Oh.
using palladium and the catalyst. This question is what is GAN?
It's an oxidation. It's an oxidation. It would.
Oxidation.
Yeah, that's the wrong one because I'm sure if this is methoxy, I need to check that out because it must be removed. So the steric ammonium nitrate is oxidizing the double phenol to the quinone. So I'm not quite sure why hydrogenation is removed. Well, it makes me suspect that this should be but it's the, I'm interested in the intermediate levels. I need to check that actually whether that protecting group is right. I would say hydrogenation is to remove the phenol. You know if you make a palladium derivative where the triflate was, you know that's going to add to the inside end of the nearest alkene because it forms a bond to where the methyl group is. So you know it's adding to that just by looking at the structure. That is forming a 6-member ring, so that's helpful. And of course, when it does that, it adds across what was the double bond there. The carbon group adds at one end, the palladium group adds at the other in a Heck reaction. Those two, if you want stereochemistry, they add on the same face as each other. So you see how this has been set up? In the second step, from that intermediate, it's doing another Heck reaction. So you form one organopalladium, it adds to the first alkene, but rather than eliminating and finishing a Heck reaction, it finds another double bond, so it does another Heck reaction. So the organopalladium you get from the first reaction will add to the second alkene, putting a palladium at the far end of where that double bond was. So we'll add across here. But then there'll be two hydrogens on the top position of the ring. So one of those will be aligned to where the palladium is to do a syn elimination and give the double bond in the product. The people at the front here were querying what the subsequent steps are. It looks a bit suspicious to me, but these two methoxy groups must become two phenols, and then steric ammonium nitrate, CAN, is there to oxidize the diphenol to the quinone. bit suspicious as to whether these methyl groups are correct. But I'm interested really in the coupling part, or the organometallic part of it. So palladium insertion into the aromatic ring to triflate bond gives you an organopalladium there. That adds across the alkene in a Heck reaction where the organic bit adds at one end, the palladium bit adds at the other end. That gives you, that forms this orangey coloured bond, gives you a palladium, a new organopalladium. In fact, it can't eliminate. There are no hydrogens on the next door position. So it couldn't finish off a normal Heck reaction. It has to be looking for something else to do. And here's another double bond for it to add to. And then it can eliminate to give the double bond back again. Does that make sense? Notice the simplification, and you can remember this when you draw these mechanisms. We don't really know what ligands are left around the palladium at that point in the reaction. So we just opt out of being exact there, and we just put L for ligand n times, meaning n is a number, we don't know what it is. You'll often see that in these cases because very often you have no idea in the intermediates what ligands are actually around the palladium. In fact, it may be more than one variation there. So when sometimes you see no ligands at all, or sometimes you see something like I've written there, which is essentially means there are some ligands, but I don't know which ones. Okay, so that's, in fact, I think that's my last, that's my last problem. So that's about when I said, I told Professor Singh I'd finish about 12:30, so that's okay. But you see there, if you think about the basics of the reactions, we haven't gone through any of the, I mean, my questions have sometimes said draw a full mechanism. And yes, you can go back to those catalytic cycles we showed and so on. But I think that wasn't the point so much of this session. It was about you recognizing the reaction. You can always go and look up what the catalytic cycle is. Well, not always, it depends if you're in an exam or not, but generally speaking, in real life, in a lab, if you're not sure about the mechanism, you can go and you can look it up somewhere, as long as you recognize what the reaction is. And that's what we've been trying to do here, to see what components you need. Okay, so that's actually the end of the course as such. There will be a 45-minute test this afternoon. You will have to write some things down. So I've got a question on each of the three topics: pericyclic reactions, reactive intermediates, and organometallics. 15 minutes on each. We'll put them up on the screen, and then after 15 minutes I'll change to the next one and so on. It doesn't require you to write an awful lot, so do think about it, and then write a little bit of an answer, but not too much, and then we'll see after that how you do. So that's all that's left to do now, and then eventually Professor Singh will give you a certificate if he thinks you're worth it. Give you a certificate. Okay, so break. See you at 2 o'clock. Hello.
We've seen that coupling palladium always attack at more hindered side. But here palladium is attacked at less hindered side.
No, it's... Oh, in the second coupling.
No, sir.
The first one is attacked at the more hindered. So the palladium's gone to the less hindered side. Oh, I see what you mean. Yeah, I think that's probably just because it's forming a 6-membered ring rather than 7-membered ring. Yeah, I'm sure that's it, yeah. fact, those reactions are reversible, because there was an example in the lecture where I showed a palladium hydride adds, reverses, adds, moves the double bond around. So even if it went to, it could be, even if it went to the 7-member ring, that's more strained. No, but I actually think here it's the 6-member ring is driving it. Yeah.
So in the last step, when there is an oxidation,
Yeah.
I think so. When the benzene is oxidized
From the double up hydroxy to the quinine.